Welcome to Inside Chips, the podcast that keeps you up to speed on the fast-moving world of semiconductors. I'm your host, Gregory Haley, technology editor with Semiconductor Engineering, and every week we'll bring you the breakthroughs, the deals, and the science shaping the chip industry. Welcome. Today is Friday, April 18th, and here's what's happening. TSMC is back in the news this week. In a major shift for the company and the industry, TSMC says it plans to produce 30% of its most advanced chips in Arizona once all 6 fabs in Phoenix are operational. Chairman and CEO C.C. Wei told investors the Phoenix site will form, quote, an independent, leading-edge semiconductor manufacturing cluster in the U.S. The company's total investment in Arizona will be a whopping $165 billion. It's a clear move to diversify away from political uncertainty in Taiwan, and it fits squarely into the U.S. national security agenda to build a domestic chip supply chain and fuel the AI economy. Wei also confirmed TSMC's first fab in Phoenix is already producing chips, and construction on the second is already complete. Meanwhile, the Trump administration launched a Section 232 investigation into semiconductors. This type of probe is usually reserved for industries like steel and aluminum. It aims to determine whether tariffs or other actions are needed to protect national security. Fortunately, consumer electronics like smartphones and laptops are currently exempt from new tariffs, at least for now. Meanwhile, export controls are tightening. New U.S. licensing rules now cover NVIDIA's H2O chips and AMD's MI308, and both companies are bracing for impact. NVIDIA says it could take a $5.5 billion hit, while AMD is projecting up to $800 million in related costs. The Center for Strategic and International Studies weighed in with a new report warning that these export controls may not hold China back in the long run. And while that debate rages, China made its own move, restricting exports of 7 rare earth elements and magnets. CSIS flagged this as a major threat to U.S. national security, especially with those materials powering everything from fighter jets to EV motors. With near total control over the global rare earth element supply, China's move adds yet another layer of tension to the U.S.-China semiconductor competition. In money and markets this week, TSMC reported over $25 billion in Q1 revenue. That's up 35% year over year, and despite trade tensions, they're sticking to a strong forecast for 2025. ASML also posted results in line with expectations, but CEO Christophe Fouquet added a cautionary note, saying recent tariff announcements are increasing uncertainty in the macro environment. There's a major tech milestone in product news this week. AMD's Venice processor officially taped out on TSMC's 2nm process. And NVIDIA is going all in on AI infrastructure, planning up to $500 billion in U.S.-based supercomputing factories, partnering with TSMC, Foxconn, Wistron, Amkor, and SPIL. There are big moves in IP and FPGAs this week. Cadence is acquiring ARM's Artisan Foundation IP business, bringing standard cell libraries, memory compilers, and IOs into its portfolio. That deal is expected to close in Q3. Intel, meanwhile, is spinning off 51% of Altera to Silver Lake, valuing the FPGA business at $8.75 billion. Intel keeps a 49% stake, and Rahib Hussain, formerly of Marvell, will serve as Altera's new CEO. Also worth noting this week, JEDEC just released the official specs for HBM4 memory. That's 2 terabytes per second of bandwidth with more flexible access thanks to double the channel count. In our special report this week, we're covering backside power delivery. It's been talked about for years, but it's now actually nearing production. It's a major architectural shift that could change how chips are designed from the ground up. Let's hear more on this from our editor-in-chief, Ed Sperling. Hey, Ed, what is backside power delivery and why do we need it?
We've basically run out of room in silicon. There are physics-based limits to what you can cram into an 18 angstrom or 14 angstrom logic chip because not everything shrinks. So moving the power delivery outside the chip provides some necessary breathing room. It also addresses another problem, which is getting power to more transistors. So everybody wants more power and more performance from these chips, especially the high-performance computing and AI system vendors. And to do that, you need more transistors. but getting enough power into incredibly small transistors is becoming a problem. So by moving the power to the backside of the chip, it solves that problem. And it simplifies the design process because you don't have to deal with parasitics like power noise and voltage droop, but it creates other challenges too.
Oh yeah, such as?
Well, first of all, you need to thin the substrate to stay within the power budget. That creates handling problems. This is manageable, but it's very expensive to deal with. And while it reduces the routing problem for both power and electrical signals, the EDA tools that have been developed to handle this complexity now have to be redesigned to deal with power from the backside of the chip. So that's a problem for the existing tools. It's a big opportunity for EDA vendors, but it's also something new that engineers need to learn.
When can we expect to see this?
Well, Intel announced plans to implement backside power delivery in its 18A process, or 18 angstroms. That's supposed to be this year. TSMC plans to introduce it next year with its N16 or 16 angstrom node. And Samsung hasn't said exactly when it's coming, but is on board with this technology. However, there are multiple versions of backside power delivery, so we're going to be wrestling with this approach for years to come.
It's very interesting. Thanks for the update, Ed. We'll see you soon. You can read the full report, Backside Power Delivery Nears Production, on the front page of semiengineering.com. Also, for a complete look at today's advanced packaging environment, check out our free ebook, Advanced Packaging Fundamentals, also available at semiengineering.com. Now let's turn to global news. Intel has decided to keep open its Hawthorne Farm campus in Oregon. Nokia will build a new photonic chip fab in San Jose, and Microsoft, Western Digital, and others are teaming up on a rare earth recycling program for hard drives. In South Korea, the government announced a $23 billion chip stimulus, covering utilities, research, and workforce development. And according to TrendForce this week, DRAM and NAND flash prices may rise up to 8% in Q2 thanks to pre-tariff inventory stockpiling. In security news, the CWE released a podcast on root cause mapping and the top 25 vulnerabilities. CISA issued new alerts on credential risks in Oracle Cloud, and Georgia Tech students won the NSA's Codebreaker Challenge again. That's 4 years in a row for the Yellow Jackets. In quantum computing news this week, QPI AI launched India's first full-stack 25-qubit superconducting system. The UK committed $159 million to commercialize quantum technologies, and IonQ signed new deals in Japan and South Korea to explore secure quantum networking and quantum encrypted satellite communications. In research news, Lam Research donated a multi-chamber etch tool to UC Berkeley's Marvell NanoFab Lab, giving students hands-on access to advanced production technology. And that's not just academic, it's workforce development, feeding the next generation of process engineers. Harvard unveiled a mid-infrared pulse generator on a single chip, compacting what used to be a bulky lab setup into something portable. This could be huge for gas detection, medical diagnostics, or even on-chip spectroscopy. Meanwhile, Harvard's RoboBee got new legs, enabling softer landings. It sounds cute, but micro-robotics like this could play real roles in disaster response, agriculture, and microsurgery. Down in Australia, researchers published a roadmap for commercializing neuromorphic computing, the kind of brain-like processing architecture that could eventually upend AI and edge computing. And in deep physics, the U.S. Department of Energy's Tesseract project is using advanced cryogenic detectors to search for low-mass dark matter. These sensors rely on semiconductor fabrication techniques, so yes, even dark matter research is riding the chip-making wave. For these stories and more, check out Semiconductor Engineering's Weekend Review at semiengineering.com. And that's all for this episode of Inside Chips. Until next time, keep your layers aligned, your yields high, and your focus on the future. I'm Gregory Haley. We'll see you next week.